Any question from the last from the Tuesday's class before we get started? 혹시 저번 수업에 대해서 질문 있으신가요? 제가 웬만한 건 다 답을 드린 것 같은데. I think I addressed almost all questions, and I actually uploaded the separate file, the Q&A file on Classroom. Yep, that's totally fine. You can use your notebook. 성준님 그냥 마이크 켜고 물어봐 주실래요? 이거 일일이 다 치시려면 시간이 오래 걸리니까.
예, 교수님, 그 수업 중에 SL에서 바이너리 클래시파이어 설명해 주실 때요.
네.
예, 그때 이제 X 도메인의 그 여러 원소들이 각각의 이미지 자체가 원소들인데 그 원소가 128 x 128인 거다. 이렇게 설명을 해 주신 거 맞나요?
그 원소들이 사는 차원이 128 x 128, 즉 16,000 차원 정도 된다는 거죠.
예. 근데 원소들 자체는 이미지 자체인 거고 그 이미지가 몇 개인지는 우리가 알 수 없는 거고 그렇게 생각하면
원소는 무한대인 거죠. 왜냐면 실수값을 가질 수 있으니까 픽셀 값들이.
원소가 이미지 자체가 원소 아닌가요?
그렇죠. 근데 이제 원소의 개수는 무한대인 거죠. 왜냐면 픽셀 값 하나하나가 실수라고 치면은 실수는 무한하니까 당연히 128 x 128의 그 픽셀 조합은 무한한 거죠.
예. 근데 제가 여쭤보는 거는 혹시 픽셀의 개수가 그러니까 RGB 이런 개수가 뭐 무한하지 않아도 이미지 개수가 무한계이면 이미 원소의 개수는 무한계인 거라고 생각이 돼요.
아니죠. 예를 들어서 픽셀 값이 오로지 0일일 수밖에 없다. 픽셀 값은 무조건 0 또는 1이다. 근데 그 픽셀이 128 곱하기 128개, 즉 16,000개 있는 거잖아요. 그러면 위에 16,000승밖에 없는 거잖아요. 가능한 원소 개수가. 그럼 무한한 게 아니죠.
네, 알겠습니다. 감사합니다.
네. Okay, so today's practice topics, it's as you can see on my screen. Can everybody see my screen? Last time there was something wrong with my computer, so it wasn't being recorded. So 화면 다 보이시죠? 네, 알겠습니다. Okay, so today's practice topics, we're gonna learn very basics of data plotting or visualizing your function, and then we're gonna generate some samples, and then we're gonna fit a line on the generated samples. Then move on to the classification, where we will first start with data loading and a bit of a pre-processing, and then we're gonna do classification and followed by some additional visualization as well. All right, so these are just, you can just load things up. So we load the NumPy, and importantly, today we have two more lines, which are Matplotlib. So this is going to be used for visualization or data plotting. Sklearn, this is scikit-learn. So this is a library of all machine learning, except for deep learning domain, I would say. So it has like support vector machines, it has decision trees, logistic regression, and a lot more actually, like clustering, visualization, pre-processing, a lot of stuff. So if you want to do some machine learning using Python, a combination of NumPy, Matplotlib, and sklearn is like the minimum requirement. All right, since you've loaded it, if you run this thing, you'll see a line. So what's happening here is that this plot function, so PLT, so PLT is just another name for pyplot. So among Matplotlib, you're gonna import pyplot and I'm just gonna call it PLT, like a lot of people do. So PLT is what we're gonna use to visualize things. So PLT.plot, this is just plotting function. So okay, and this is your x-axis. So this is your x X element in your 2D plane, 2D plot. This is your Y element in your 2D plot. And then you're gonna, actually, let me just try this one first. Oh. All right, so if you comment the second line out and then just run it, then what do you see? You see a line, right? But if you comment the first line out and then execute the second line, you see 3 dots only. So, but you can see that the arguments are the same. It's just 1, 2, 3, 3 to 1, 1, 2, 3, 3 to 1, and both represent the X element of your data, and this is your Y element of your data. And it's just different ways to visualize your data. So one is plot, meaning it's going to be a line, and this is just scatter, means you're going to scatter plot your samples. So you're going to get the same number of dots as the size of your samples. Not really for plot. This is you're gonna draw a line along your plot. So if you try something out, like if you add 10, maybe 10's a bit much. Maybe 6, and 6 here. What are you gonna see? Yep, like this. But if you add 6 here and 6 here, this is what you see. So I'm just gonna you're overlapping the plot with the scatter plot. So there are 3 dots. Well, I'm sorry, 4 dots, and so scatter plot will just simply plot them, scatter plot them on the 2D plane. The plot function will draw a line along the plot, draw a line along the samples. So yeah, you can play around a bit with this, and there are a lot. So this is the very like the core. No, it's still a real number. It's just that there's probably not enough space to show them. Yeah, it's just probably you don't have enough space. Even if you use 6 dot here, let's see what happens. Yeah, it's still so. Yeah, the numbers on the axis, the y-axis and the x-axis, they are still real numbers. It's just that there's not enough space to put all the subdecimal numbers. Oh yeah, show is without show you're not gonna see it. Oh, actually, so this is Colab notebook. So even without the show function, it's gonna actually draw the picture. But when you're actually writing codes on your IDE like PyCharm or your Vim or whatever text editor that you use, without actually using the show line this here, you're not gonna draw the picture. So here the picture is automatically drawn because it's Colab notebook. So yeah, show is actually showing the plot. So, okay, as I said, this is the minimum requirement: plot and show, or scatter and show, or actually there are a lot other different types of visualization. There's bar charts, there are pie charts, there's I don't know, there are probably a lot more charts, like horizontal bar chart, vertical bar chart, maybe 3D plot, 3D scatter, and all that. So if you're interested in that, you can go to Matplotlib website, and then there's API document. Even I don't know all the things there because I usually use only the plots and scatter plots. But that if you want to draw something and if you have an idea, you can search things on Matplotlib website. All right, moving on. Oh, and I forgot to say that there are a lot more. You can put a lot more meta information, such as, let me just draw a bit more stuff. So X label, if you use, this is x-axis. Yep, this is what happens. So this is x-axis, this is y-axis. You see here, and you can even control the size of the text and maybe the font of. Maybe you can choose the fonts as well. I'm not really sure. Not really into like the aesthetics, but yeah, basically you can control anything, almost anything you want on your plot, on your visualization. Right. All right. So Matplotlib cheat sheet. Yeah. Thanks, Wilmer. Yeah, that will be helpful for a lot of people, maybe even for myself. All right, moving on to the next cell. So here, this is just a function for drawing things, and it's a bit looking weird. There are 4 arguments, and you will see why I specifically define the function like this. So if you take a look at it, just going through all the the samples in the x and y and plotting it. So it means that you can actually plot a lot of stuff. It doesn't have to be just one plot and one scatter. It can be it doesn't need to be the same number of elements. See here that you can draw a lot more lines, not just one, but 2 or 3, even like a lot of lines on the single chart, single plot, a single figure. So that's what's happening here. It's just if you give a list of elements on x and y, then it'll draw everything on the plot. Then it scatter plots the samples given for x sample and y sample, and then they're just labels. Oh, these are what's happening here. Let me just draw that again. I'm just drawing a grid line for the on where the x value is 0 and y value is 0. So I'm just drawing the x-axis and y-axis in the Cartesian coordinates. Right. All right. So we'll get to use this draw function a lot today. Can PLT handle more than one plot? Yeah, I think I just showed you here. 1 plot, 2 plots. It doesn't have to be just the plot. You can, put scatter plots as well. Oh, wrong. Oh, yep. So, see, on different canvases. Yeah, you can use something called subplot, which you will be doing today. So there's one of the quizzes in the later stage today is using an API called subplot. So you can draw plots like simultaneously, like side by side, basically. I think you can see it on the bottom. I think I've included a screen capture of what you should be seeing after you've filled in all the codes. Moving on. So here, this I hope you're familiar with the Lambda function in Python. So foo is a function. What is the role of the? Yeah, you'll get to see that what's happening. You'll get to see. All right. So here, foo is a function, and I'm using something called linspace, which I didn't explain last time, but actually you can try it out. Maybe see. Let me just quickly go through what that is. So x is np linspace 0, 10, 100, and let's say that y is the same thing, and I'm gonna scatter plot them. What do you see here? You see, let me just crank it down to 10. Yeah, so linspace is used for drawing samples on the line, which is start, end, and 10 samples on the line, and evenly distributed samples. It's not just randomly sampling on the 0 to 10 range. It's evenly sampling. So there's 1, 2, 3, 4, 5, 6, 7, and y is the same thing. So that's why you see a line. And of course, if you draw a plot, then it'll be a line. Right, so that's what linspace is for. So you have linspace and you have some function. So please draw using PLT, using plot or either scatter to see what the function looks like, the function foo. Can you do that? Yeah, exactly. And the Wabi. Oh, even yeah, Junmin used the draw plot function that I just that I defined. Yeah, actually, that's what I was supposed to tell everybody. So all right, I'm gonna try something out. So y equals foo x line, right? So this at least you need to put the line on the function to get the y elements. So this becomes y line, and if you just simply draw like Wabi, actually Wabi used a bit of a trick to make a red line right here. And if you use draw function, draw plot x line, y line, x line, y line. I think there could be a syntax error if you do this. Yeah, you get a syntax error because if you remember, draw plot receives big X and big Y, and it goes through the elements of the X. So each X, it should be a list of lists, basically. So you should encapsulate your X line and Y line with a list. So I'm still, all right. I didn't do this. Actually, then let me go back and see what happens if you remove the. So, okay, so this is not what you should be seeing. If you do like this, oh, it's still the same. Okay, I guess it doesn't really matter. Anyway, so yeah, this is what you get to see. So, okay, there is a line. Okay, so you can see that there's a very tiny line here. Like you can see the line here. This is the effect of using the plot, and the dots are the effect of using the scatter API. 네, 맞습니다. 네, 경현님 맞습니다. 정확히 그 얘기예요. 이렇게 하시면 라인이 안 생기죠. 네. So what you can try is you can put X line here, and maybe we can switch the places. Add one more line or add one more plot. Let's see what happens if you do this. Yep. So there are two lines. So there should be a line behind all the dots, and then there's another line because I just added one more line element in the big X and the big Y. So, right. So this is what that function is for. Draw plot is for. All right. So draw the function foo using X line. Now sample 5 points of foo in the domain 0, 10 and visualize with draw plot. So do you know how to sample points of foo in the domain 0, 10? So here we were using linspace 0, 10, 100. So there were 100 elements, right? But we don't want 100 elements. We only want to use 5 points. So use linspace. I forgot to say that using linspace. 7 points of foo using linspace sample 5 points. So we did this. All right. I hope that everybody's getting the same 0, 10 instead of 100. Should be fine with 5 now. Then Y sample, X sample. Then you just simply draw. Then you see only 5. 1, 2, 3, 4, 5, right? And let me actually, so in order to explicitly show to the user that we are drawing from, oh, actually, I maybe should have been the other way around. Oops. X sample, Y sample, maybe put, just to make sure that we are demonstrating to the user that we are drawing 5 samples from this line. So the original function looks like the sinusoidal function. Well, it's not actually a sinusoidal function because, as you can see, it's a polynomial function of degree 3. So it's a 3rd order polynomial function. So, and we are drawing from this original function 5 points from in the range 0 to 10, evenly distributed, right? Now, what you want to do is you want to add some noise to the sample, basically Gaussian noise. So sample 5 points of foo in the domain. It's the same thing, but you're just adding noise where the noise is coming from the Gaussian distribution where mu is 0, sigma is 0.1, and then visualize. Can you do that? I'm just gonna give you maybe a couple more minutes. 일단 박경현님, randomly sample, 뭐 사실 X랑 Y 전부 다 노이즈를 주셔도 됩니다. 저는 근데 개인적으로 저는 짰을 때 X는 그냥 똑같이 뽑고 Y에만 랜덤 노이즈를 줬고요. To YH ton, so that it is almost correct. Actually, let us try that out. Let us try what YH ton did. All right, so now the X elements are not evenly, distributed because there are noises injected to the X. But the problem with this is that the same noise is added to all the samples and all the X samples and all the Y samples. Well, you already did. So that, yeah, I mean, I was thinking about adding noise to the Y sample only, but that's totally okay. Adding, let us, without, so something like, the problem with, yeah, I mean, that's okay. You adding noise to both X and Y, or maybe only to the Y, that's fine. The problem with your code is that it is using the same noise on all elements, on all 5 samples. It's using the same noise, so it's not actually a noise. It's a determined noise. All right, so Soro and Junmin, they are sample shape, random normal, example for sample net noise. Y sample is Y sample plus NP. I'm not sure where the large Y sample is coming from, Soro. All right, but I think everybody's getting the point. So let me give my example. So 1.5. So I'm just going to have a separate variable named num point. So 5, and without this. So instead of using, when you use 0.1 as a standard deviation for your normal distribution. So what do you see here is, let's see. So y is what? Y is the one-to-one corresponding elements for the x samples, and I'm just adding noise here when I'm drawing, when I'm putting the x elements into through the function foo. I'm adding noise here inside. I think there should be like this. And then if you draw this, there's not much noise going on, to be honest, because the standard deviation is only 0.1. But if you use standard deviation 1, then the noise is too big, basically. You can't, just by looking at 5 samples, it's really hard to see this is a polynomial function of degree 3, right? Graph of second quiz is affected by a qualification code in third quiz. No, do you mean this one? Do you mean like this is being affected by this? 네, 그러니까 한 셀 안에서 여러 번 그리시면 안 되고 이거를 당연히 한 번씩만 그리셔야 됩니다. 그러니까 지금 이걸 2번 부르시면 draw 플롯을 2번 부르시면은 똑같은 그 하나의 공간 안에 플랫이랑 스캐터 여러 번 하는 거거든요. 그러니까 이제 그 계속 겹치게 되니까 기본적으로 서브플롯을 이용하지 않는 이상은 캔버스는 하나입니다. 캔버스는 하나고 그 위에다 다 그리게 되는, 누적해서 그리게 되는 겁니다. Alright, so I just explained that without using some special functions like subplot or something like that, you basically have only one canvas, and if you draw anything, if you do plot or scatter and all that, then you're using the same canvas again and again and again. So all your previous plot functions and scatter functions will have cumulative effect on your final canvas. So in a single cell, you should use draw plot only once. All right, so as I said, so what the I think 0.3 would be a nice standard deviation to make the problem just a bit harder than giving 0.1 standard deviation. So looks like, if you look at this, if you look at 5 samples, then you can kind of see that this is a polynomial function of degree 3. So that's what I'm trying to generate, because we're going to use this function, use these plots. I mean, use these samples, the 5 samples, to do regression from now on. Okay, should we add the noise in the inputs or outputs? That's totally up to you. If you want to make the problem, I mean, it doesn't even have to be. I can add. Yeah, you can add noise here as well. NP random, random, normal, something like this. Yeah. And then the x samples, the x elements won't be evenly distributed. Here it's 0, 3, 6, no 0, 2.4, 2.5, 5, 7.5, 10, because it's evenly distributed. But if you start adding noise to the x elements, then it won't be evenly distributed. But that's still okay. It's still okay. But basically it doesn't have really a lot of difference to when learning a regression function, because where you're located has less impact than the actual corresponding y value. If you add too much noise to the y value, then it's basically you're destroying the shape of the function. 홍기훈님 그렇게 하셔도 전혀 문제 없습니다. 네, 그렇게 하셔도 되고. 맞네요. 제가 실수했네요. 죄송합니다. I'm sorry. So 홍기훈 just corrected me. Yeah, this it should be this way. Because yeah, I'm sorry. So you're putting the x samples through the function first, and then you should add the noise. The previous way wasn't the correct way. So I'm sorry about that. So yep, and something's definitely wrong here. Well, because I have this one, so forget about this. Yep, and maybe 0.3 is just not enough. Yeah, it's there's not much errors going on. This looks interesting. Maybe 2. Okay, this is a bit, yeah, all right, maybe 1.5. Yeah, just to spice things up. We don't want to completely destroy the picture, right? All right, 원우 조. Oh, you can use plot close after plot show, just to destroy your previous canvas and renew your canvas. Sample values are added to the parameters of who it is it intended sample values added to. I think I just corrected my my mistake. Thanks to 홍기훈. Yep. 아, 그거는 그러니까 이제 잠시만요. Y 샘플이 왜 그러게 왜 벗어난 걸까요? 아, 그렇죠. 왜냐하면 여기 X 샘플은 여전히 그 랜덤 노이즈 넣기 전 X 샘플이고 Y 샘플은 X 샘플에 랜덤 노이즈 넣은 다음에 foo를 통과한 거니까 서로 얼라인이 매치가 안 되죠. 서로. 그러니까 이 X 샘플에 Y 샘플이 그 X 엘리멘트가 맞질 않는 것, 얼라인이 안 돼서 그래서 벗어나는 겁니다. 플랫 타이틀이 레전드도 플랫 타이틀 플랫 레전드로 매트랩과 동일하게. Yeah. So the question is the plot title and plot legend the same as PLT title and PLT legend in MATLAB? And I'm not really sure because I haven't used MATLAB in a long time. But basically you can add titles and you can add legend as well. You can add like PLT title, and then suddenly your plots will have title like this, title. And then if you add more plots, then if you use legend, then each plot will have its own denotation, some color, and then the legend box. All right, so I hope, okay, so 1.5, all right, we'll be using, so we put X sample through the foo and then add noise here, and then we're going to use standard deviation of 1.5 just to make things more interesting, like this. So all right, so from now on, this is the X sample, this is Y sample, and we're going to reuse it all the time throughout the regression. So here, what's happening here is now we're going to linear regression, and you're going to call a linear regression function from sklearn, scikit-learn. So as I say, scikit-learn has a lot of stuff inside, and among a lot of stuff, there's a sub-library called linear model. And under linear model, of course, there are a lot of stuff as well. Linear model underneath, there's probably like, I don't know. I haven't really delved into linear model library, but basically it's suffice to say that linear regression lives inside linear model sub library. So we're going to call that. And it's really easy. Actually, all scikit-learn models go through the same step. You just define, you call a function, you call a model. So linear regression without any parameters. I mean, you can specify certain stuff here actually. Let me actually go through this. sklearn linear regression here. All right, so you'll have to visit this page a lot when you're using scikit-learn. So there are certain things that you can, certain arguments that you can give. So when you're initializing, so this this is basically a constructor, right? So this is a constructor, class constructor. So inside the constructor, you can give some initialization arguments like fit intercept. So you're gonna well, if y equals like x plus b, then b is the intercept. So if you want to use the intercept or not, and normalize if you want to normalize your inputs or not, and some options basically. So, but we're not going to use any of those. We're just going to use the vanilla linear regression. And if you once you've defined it, once you've constructed your class or instantiated your class, I'm going to call it LR, following linear regression. You have to fit your stuff. You have to fit your or train your model given samples. So fit is training, like optimization. So, and in order to train your model, you need to give X samples and Y sample, X and Y. So X being the sample, Y being the label. So we already have these, right? We already have. Oh, by the way, I haven't actually explained this. So you want to fix your random seed to 0, so you get everybody gets the same result. Like we're going to compare results in the down state, in the later stage. So please use random seed 0 in the previous slide, and previous, like in the upper cell. Use this, and then we're going to use this these samples from now on. So NP random seed 0, and why do you add new access to X sample when fitting? That's a good example. I mean, that's a good question. Here, what's happening here is that actually what I'm doing is I have only one pair of X and Y. Here, there's only one X sample, which is 5 plots, and Y sample, which is also 5 samples. So that is just, I have only one pair of sample to fit a line. But if you remember, there should be a batch of samples. There should be a lot of X samples and a lot of Y samples. But here, I just only have one X sample, one Y sample, and the training function is expecting you to give a batch of samples. So that is why I'm adding an extra dimension here. Oh, I'm sorry about this. Forget about what I said. So I'm sorry. This this is just this is totally crazy. I'm adding one. Let me see. So if you don't have this, if you just give simple X sample here, you run into syntax error because you only have a single feature. So this is X is just 0, 2.5, 5, 7.5, 10. So it's a single feature. It's just a single real number. It's not a multi-dimensional feature. So that is why you want to make it into multi-dimensional feature. I mean, fake multi-dimensional feature. So this, by having a none, by adding none, if you remember from the very first practice, if adding a none is like expanding your axis by 1, right? So this is exactly saying that even though this is a single dimensional feature, I'm going to treat it like a multi-dimensional feature, because basically your fit function is expecting for the first argument to be a matrix, and the second argument to be a vector. So vector being one label per example, but here X sample needs to be a matrix because one row should be a sample, if you think about multi-dimensional features. So that's what's happening here. Seed 0. So okay, so seed 0. If you without seed 0, actually, let's just try it out. You try this multiple times, and each time your plots will look different. I mean, your scatters will look different. Because you're randomly drawing samples from the normal distribution. So your dot, see the location of the dot, they change every single time you run the cell. But if you fix your random seed like this to seed number 0, then every time you rerun the cell, it's exactly the same dots, right? Yeah, and we're doing this because I want everybody to have the same X sample and Y sample so that we can compare results in the future. And yes, it doesn't have to be 0. It can be any number you want. It can be 1, 2, 3, 4. It can be like 10,000, 5,000, 6,000. Doesn't really matter. I'm just using 0, so I'm just hoping that everybody's using the same seed. Exactly. So yeah, Jisoo put it very succinctly. That's what I'm doing here by adding the none term here. Yep. All right. So once you're only giving 5 samples to linear regression. So it's the training phase will be done in an instant, and then here what I'm doing is I'm using a score. So once you fit your function, you need to evaluate. Like there was accuracy, there was like precision and recall, FID score, blue score. Here I'm using something called R squared. So R squared is, if you go to Wikipedia, you'll see what R squared is. Basically, it's how you're doing better than just than just simply predicting the mean all the time. So here, given 5 samples, what is the mean value of the 5 samples? It'll be, if I can annotate, the mean of the 5 samples is probably somewhere around here. So so R squared is basically trying to see how well your model is doing then compared to this mean line. So obviously you want to do much better than that. Y 샘플은 벡터여야 돼요. Y 샘플은 이미 벡터잖아요. Y 샘플은 이미 벡터니까 fit 펑션에는 so the question is you don't need to expand your Y sample because it is already a vector. It's a one-dimensional array vector, and fit function is expecting the second argument to be a vector. So that's because you want to have one label per sample. Of course, that's just logistic linear regression. Yeah, if you want to do multi-class classification, that's a different story, but we'll get to that later. All right, so as I said, R squared is just a relatively how well you're doing compared to just predicting the mean value all the time. So let's try it out. Well, what am I doing wrong here? All right, let's just comment this out and see. So your R squared is 0.52, and if you go to R squared, which is another name of this is coefficient of determination, and you see here that Y bar is the mean value of Y. So basically, it's a relative term. So if this is always predicting the mean, and this is your prediction from the function, and it's a ratio between the two. So if there's zero error on the top, on the numerator, then your R squared will be 1. But if the error is the same, if the numerator and denominator are the same, that means like your function is generating the same amount of error as just simply predicting mean all the time, then this will be like 1 because it's a ratio, and then your R squared will be 0. So the maximum value of your R squared is 1. So you want to reach 1 in your regression, and unfortunately this is not 1. This is 0.5279995. It's not a cost function because the cost function is when you train linear regression, it is trained by mean squared error, MSE. So mean squared error. This is mean squared error. This here. Oh, I can't. Okay, I can. I'm sorry. Yeah. So the second term here. This is mean squared error, and your logistic or your linear regression is trained by using mean squared error as the loss function. The loss function that I described on Tuesday. But you evaluate your model not using MSE because it's it's not very intuitive. You're using R squared, the coefficient of determination, to evaluate how well your model is doing. And MSE doesn't have MSE doesn't have an upper bound. It does have a lower bound, which is 0, but you never reach 0. So, but here R squared does have an upper bound. Like 1 is your upper bound. You can't go beyond 1 because 1 is like perfect. It's a perfect regressor. All right, now predict. So what you can do is you can predict a single data point. So once you've trained your model, you've already fitted your model, right? So once you've trained it, you can you can predict for a single sample. So there's X sample, and if you run this, I'm sorry, there should be another. Still, you should give none. What am I doing here? Okay, so I should have done this maybe. All right, so what am I doing wrong here? X none. Yep, thank you. Thanks for the assistance. So none. Yep. Okay, now yeah, right. If you print this value, actually, we should print both values. So corresponding value of 0 should be, actually, it should be here, right? It should be 10. But unfortunately, is it 10? Yeah, it should be 10. But now it is showing 3.5, so which is really wrong, right? So it means that it's somewhere over here, the prediction. So it's a large error. Now you want to calculate. I guess we can do that. Calculate the mean squared error using x sample, y sample, and LR predict. So I just gave you the answer. This is mean squared error. And given this equation, can you calculate the mean square error between using x sample, y sample, and the prediction? So you want to put your x sample through predict, and then you get the y samples, corresponding y predictions, and then given the x samples and the y predictions, can you predict the mean squared error between the two? Just to give you y sample, y hat. Oh, NP subtract. Yeah, you can do that. Y hat, y sample divided by len x sample. That's also correct. That's also correct. Yes, NP squared. All right. So a lot of people already, we have 2 correct answers. Using dot mean is the same as dividing your summing up and then dividing by the number of samples. So let me just copy paste mine. Oh, maybe I should have done that. All right, so this you put your x samples through the predict function to get the y hat, and then you basically do the same as other people like Wabi and Jun. You can use like minus and like star to denote as a substitution for subtract and square. Yep, Jung Jong-ho was smart enough to use the API provided by Sklearn. So your MSE is function foo and the line. Yep, your MSE's, it's a whopping 76, which is just, yeah, this is just unacceptable. MSE number, MSE of 76 is just, usually when you do machine learning, you get to see MSE of 0 point something, basically absolutely subdecimal. So linear regression is not doing a very good job. Now the final quiz is to use Xline, LR predict, and draw plot to visualize the linear regression model. So you have trained your linear regression, and you want to see what is actually approximating. And you don't want to use just 5 samples to scatter plot. You want to use the Xline to see what's happening to the linear regression. So you want to use Xline, and Xline, which was defined here, Xline, right? So it is 100 samples between 0 and 10, evenly distributed. You want to use that. And then put it through the predict and get the corresponding y sample, y elements, and then use draw plot. Very simple, right? All right, I'm gonna give maybe 1 more minute. Basically, you want to have this. X line is coming from the previous cell, X line, Y line, both are coming. So Y line was also here. It's X line just put through the foo function. So X line, Y line, you want to have X line and Y LR, which you can simply get by doing LR, Y LR equals LR predict. X line, and I probably need this. An X sample and Y sample, X sample and Y sample are coming from here, X sample and Y sample. So if we draw this, you get this. So what's happening here? So the dots, the 5 dots were sampled kind of with added noise from this true function, which is the blue line. And the linear regression is trying to approximate to the best of its effort to fit a line using five dots here. So which looks pretty reasonable. The orange line is the what linear regression is trying to approximate. And you can see that at least the lines are, it's going through, it's piercing through the 5 samples in a reasonable manner. But it is just, linear regression is just the power of the linear regression is too weak to properly approximate this true function, which is at least 3rd degree polynomial function, right? So you can see that this is what? Is this function, is linear regression underfitting or overfitting in this case? Yep, it's underfitting, exactly. So what we're gonna do is we're gonna try to make it fit nicely, and even go beyond fitting nicely. We're gonna try to make it overfitting. So that's what this cell is for. All right, we're gonna actually use polynomial function from now on. So in order to use a polynomial function, you need to import something called polynomial features. So basically what you're doing is you're transforming your features using this a function called polynomial features. So polynomial features class will transform your feature into like 2nd degree, 3rd degree, or 4th degree, or whichever degree you want. And then once you've transformed your features to a degree of your liking, you can train a linear regression function on top of that, which will now be essentially a higher order polynomial regression function, because your features are higher order. So that's what I'm going to do now. So you instantiate a polynomial features class, and I'm going to set the degree to 2. Of course, it can be any degree, but we're just going to start with degree 2. And then you transform your features, which is X samples. You transform your features using fit transform, and then now your X sample poly would have a 2nd order features from now on, because before it was 1st order feature. It was just 13 minus 3, 13, 34, 26 maybe. But now it's X. Actually, we can let me see what it looked like. Once you've transformed it, now it has 3 elements per sample. Before it was one. Maybe I should to make it into a matrix. So before it was just 1 element, 0, 2.55. I'm sorry. Yeah. Okay. I'm sorry. Yeah. I just calculated, like when I said 13 minus 3, it was y elements. I should calculate. I should have iterated 0 x elements, like 0, 2.55, 7.5, 10. So that's what it is. 0, 2.55, 7.5, 10. And you're expanding the feature space, the dimensionality of x element, into 2nd order polynomial space, which is 3-dimensional. So now you can see that 0, 2.5, 5, 7.5, 10 is here, and this is 1, 1, 1, 1, 1, because the raising these elements to the power of 0 is all 1, right? So this is power of 0, power of 1, and power of 2. So if you square this is 0. If you square this, you get 6.245. If you square this, you get 25, such and such. So that's what fit transform is doing underneath. All right. Now you fit your linear regression function. So I'm just gonna, I'm just gonna use the dot expression, your dot fit X sample poly and Y sample. So you will fit your linear regression function on the 2nd order polynomial features. Now, can you visualize this new LR using the X line like this? You want to do the same thing as this. Can you do that? All right, I'm going to give you maybe a couple minutes. So unfortunately, there is no model called polynomial regression in Sklearn. When you're using Sklearn, in order for you to do polynomial regression, you have to use polynomial features to first transform your features into second or nth order polynomial feature. So you're transforming your features to this via fit transform into a polynomial degree of your choice. So basically, as I've shown you using these print functions, you're transforming your features into nth degree polynomial space. And then once you've done that, you're using that transformed features, you're plugging that features into linear regression. That's how you do polynomial regression in Sklearn. There is no like polynomial regression class in Sklearn. 일차일 때만 엑샘플의 영승 필요합니다. 그거는 여기에다가 1을 넣어보면 알 수 있죠. 네. 그러니까 아까 영승을 없는 건 그냥 제가 그렇게 만든 거고. So the question is, I'm not sure how to interpret that question. So there was no one, like the ones, which is the element corresponding to the 0th power. This doesn't have that. The original example doesn't have that because I didn't put them inside. But if you use fit transform to the first order polynomial, then you suddenly see these ones because you need the 0th power elements anyway. 그렇습니다. 네, 경영님 그렇게 맞습니다. 그 피팅은 언제나 어차피 민스퀘어 에러로 하기 때문에 피팅 펑션 하나만 있으면 되거든요. 그러니까 이제 피처를 불리는 거죠. I forgot to. All right, once you've learned that, I hope that everybody's at least, seeing what they've learned using the visualization. So I'm going to copy paste my version here. What's happening? So here I'm using fit transform. Sorry. So what I want to do here is that I want to compare with the original function and the learn function. The original function, the foo function, and the learn function is the LR here. Actually, let me call this poly because this is no longer linear regression. No, this is polynomial regression. Maybe PR. Yeah, okay, PR. Instead of LR, we're going to use PR. Oh, come on. All right, PR. And then this is going to be, so you first of all, when you want to compare the true function and the fitted function, you need to transform your original X line to the second order polynomial space because you want to draw it on your space as well. And so X line poly and then Y poly, and you basically you fitted your polynomial regression function PR, and then you are predicting it using X line poly. And then you're drawing it with the same draw plot function. So here, what's happening here is that so the original function is this still is the blue thing, and the samples are the same samples like before. And now this orange line is the function is the polynomial regression function that you fitted with the 5 samples, and unfortunately the degree is 2, so it has to be quadratic. So it's not really fitting very well, See, it's doing a better job than linear regression. It's doing a better job than linear regression from the previous cell, but it's still not as satisfying as we hope it to be. Yep. So Yuanjun says degree 3 fits well. Obviously, it should fit well because the true function foo is a third-degree polynomial function, and if you use degree 3 here, then you're using polynomial function of degree 3 to fit the true third-degree polynomial function. So that's enough power. That's all the power you need, actually. Raising this to 3 will give you this. And because we injected some noise, the Gaussian noise to the samples, so that is why it's trying to fit to that noise. So it is not following the true function. It's not, there's a gap between the true function and the fitted function, because the fitted function is learning from the noise added samples, right? What happens? So another quiz is, what happens if you decrease the degrees of the polynomial? So it's just easy to do that. Let's try 4. Still looks okay. 5. Yeah, it starts to deviate a bit. And if you raise to 6, now it's deviating a lot. And 7, yep, it's weird. 8, yeah. So you can see what's happening here. It is, if you use, at least by using degree 6, you can already see that it is overfitting. It is overfitting. So when you have new test case, unseen test cases generated from the blue line, which will be like here, like let me draw some unseen test cases. So like, for example, if there's unseen test cases here and maybe here with some added noise, then the orange line, the gap between orange line and the test cases are this gigantic. So it is overfitting now. But you can see that raising to the power of 4 or 5 was doing a pretty decent job still, because the power wasn't enough to super overfit. So if it was 4, it was doing still a pretty decent job. 5 was a bit iffy, but 4 is okay, I guess. So the lesson is, it doesn't have to be exactly 3. It's like, if you go a bit overboard, if you raise the power a little bit beyond what's optimal, it's still okay. And if you're interested, you can use regularization. I won't go into that because we don't have enough time. But if you can use higher order, you can use like degree 7, degree 8, or degree 9, and then use regularization on top of that to see if it is actually behaving nicely. So adding regularization, you can do that from, I think you can add that to the fit function maybe. No? Oh, sorry. Okay, I guess there's a separate class for L2 regularization. So linear regression is linear regression. If you want to do L2 regularization, like the ones that I explained in Tuesday, you have to use ridge regression. But everything is, so ridge regression, there's L2 norm here. But everything is the same. You still define a function. You still define a class here, ridge, and then you fit it, and then you predict it. Actually, let us maybe yeah. Forgive me if I go a bit longer than like exactly 1.5 hours, but we should maybe try that out. See what happens. PR equals, I should import sklearn linear model ridge alpha is the lambda in the previous class. It's control variable, how much you want to penalize your model from having too much coefficient magnitude. So I'm going to set it to 0. I mean 1.0, and then I'm going to fit it to x sample poly and y sample, and so this is ridge regression, so RR, and then y ridge equals RR predict, and then draw plot x line, y poly, y ridge, x sample, y sample. Let's see what happens. Oh, come on. Okay. So I'm gonna raise the degree to 6. 6 was already overfitting, right? So 6 was overfitting. Okay, it's still overfitting. So you can see that 6 is still overfitting. I guess if you penalize it a bit more, maybe use 10. Let's see what happens. Okay, so now it is not as deviating like the orange line here. So let me draw a legend somewhere. Let's see what happens. PLT legend, and then go down. Okay, there's no legend because I'm not giving any labels actually. All right, forget about the legend. But you can predict that this orange line is the poly line, and the green line is the ridge line. And you can see that the ridge line, because I've increased the penalization factor, which is the lambda variable. Before it was 1, and there wasn't much difference between PR and RR, the linear regression and the ridge regression. But if you increase it to 10, then now it is being penalized. So it is, it can't have as extreme wiggliness as the original polynomial regression. If you raise it to 100, it is almost behaving like a 3rd-degree polynomial function, but it doesn't have enough power now because we're restricting the power of polynomial functions. So it doesn't have enough power to hit this sample here. So it is actually deviating. So I guess maybe 50. Still no, maybe 20. Yeah, it's really tricky. It's trying to get just the right amount of lambda variable. It takes a lot of trial and error. But you can see that what the regularization is doing to the polynomial regression function. Yeah, you should actually set a label somewhere. Yeah, I'm not really an expert in Matplotlib actually, so. Yeah, you should give a name somewhere. Like first plot, name of the first plot is RR, the name of the second plot is LR, and name of the third scatter is like scatter something. When you, yeah, if you Matplotlib plot. Is there a name here? Not really sure what. Oh, here's a label. Okay, you should give something called label, right? So when you're defining your plot, you should use label and something. But since I'm going over the for loop, I have to be really smart about giving individual labels to the plot. So I won't go into detail. But if you use label in your plot or scatter, and then you use legend, maybe I can give you a simple example. Label scatter. Then there's scatter here. So the blue dots are a scatter. And then if you define individual labels for the blue and green, like RR and LR and linear regression, then you will see like the corresponding color and its label. Hope that's clear. All right, so moving on to the classification. So we only have 15 minutes to go. What we're going to use for classification is something called iris data. So iris is part of the flower, actually, iris data. Oh, there's even a Wikipedia page. So iris flower data. Yep. So there are 3 classes in your iris. Can I see yeah, here you go. Okay, so the number of instances, so the training samples, the size of training sample is 150, and then the number of features, the attributes, number of features are 4, so it's a 4-dimensional feature. And the classes there are 3 classes. It's either iris setosa or iris versicolor or iris virginica. So there are probably different species or different types of iris flowers. So what is iris actually? 붓꽃. So 붓꽃이네, 붓꽃. It's a type of flower. So, and there are like subtypes of flowers. So it's subtypes of flower. And you want to classify which type of flower you're seeing based on these 4 features, which are sepal length and sepal width, petal length and petal width. So sepal is, I think sepal is 꽃받침 and petal is 꽃잎, right? So different parts of the flower. So depending on the, 그러니까 이제 그 꽃받침의 크기의 길이랑 크기, 그다음에 이제 꽃잎의 길이랑 길이랑 뭐라 그래야 돼? 굵기인가요? 뭐 그거 가지고 이제 이게 어느 붓꽃과냐를 이제 맞추는 겁니다. So depending on the length and width of certain parts of the flower, you want to classify into three classes, and you have 150 examples. So, and then you want to train your classifier based on the 150 examples. Actually, I was hoping that everybody can download iris data and then. Yeah, I'm sorry. I should have been more prepared. I mean, I should have moved this class faster so that you can actually download the iris dataset and then upload it, and then access it. Okay, that's kind of unfortunate. All right, let me give you a look at. Right, so that would be kind of if you already know that, then that's fine. But I was hoping that everybody can get a practice on how actually going through line by line the iris data and then creating a matrix of your own. But you can load your data set from my iris. Okay, just let me give you a peek at what the iris data set looks like. I'm gonna share, resume share, new share here. All right, so this is my terminal, and I've downloaded the iris dataset, and if you open it, it looks like this exactly. So there are 4 features. Fine. So the features are separated by the comma. So there are 1, 2, 3, 4. So there are 4 features, and the last column is the class. So it's iris setosa, iris versicolor, and iris virginica, and there are 150 samples, right? So basically, you want to go line by line reading this, and then splitting it by comma, and then taking the first 4 elements as the feature and the last element as the class. So that's how you load your data set into a matrix and a label. Oh yeah, thanks Federico. I guess because in the interest of time, we're going to skip this one. But if you're interested, it's a really easy couple of lines of code. But yeah, you can let's just try this out. Let's just load your data set. We're going to add a new code. Copy paste this. So you can just simply copy paste. I think people already did that. Yeah, copy paste. No, I'm sorry. Copy paste this, please. You need to set return XY true. All right. Yeah. All right, just like this. You add a new cell right below this one. You add a new cell, and then you load your iris dataset. So from datasets, there's a function called load iris. You load iris, and please set your return XY equals to true. So you don't want to just load. You want to load in a separate variable, the x being the features and y being the label. So once you load it, I'm going to add one more code, and just to show you the shape. So the shape of the x is 150 by 4, of course, because there are 4 features and on 150 samples. And the y shape is, of course, 150. Yep, so that's it. So moving on, so you want to use, so you need to split your data set into train, test, and validation. But here we won't be using validation because if you're not doing deep learning, if you're using simple models like logistic regression or support vector machines, you don't need the validation step. And no, that's not exactly true. If you want to tune your hyperparameter, you need to use validation step. But here we're not going to tune the hyperparameter, so let's forget about that. So we're just going to have a train data set and a test data set. And the way you can easily split them, you need to split them randomly. You can't just take the first 100 samples to be the train and the remaining 50 samples to be the test, because only the first 100 samples consist of only the first 2 classes, and the remaining 50 samples coming from all the other different classes. So you want to, you want to evenly, you basically want to do IID, independently, identically, distributed. So you want to randomly split your data set, and this function, sklearn.model_selection.train test split, this function will help you do that easily. So you do this train test split, and then you give the original x features and the y label, and you set the size of the test. So how much percentage you want your test size to be. So I'm using 20% as test size, and then this is the random state. So this is like a random seed, like this random seed determines how randomly the train and the test data set are split. So all right, so I'm going to use 20% test data. Yep, and this is good. Now you have logistic regression, which is a binary classifier. But note that this is not a binary classification because there are 3 classes. There's 3 types of flower, right? Test size explain again. Oh, so this is just the percentage. Like if you have 100% total data set, and if you use 0.2, then it's what you're saying is, I want to use 80% as a train set and 20% as the test set. And random state is how you randomly split your train set and test set. So if I can draw this. So this is your entire data. Let's say it consists of 1, 2, 3, 4, 5, 6, 7. And maybe 3 more to make it into 10. So there are 10 samples in your entire training set, right? And then if you want to randomly split into 80, 20, so you don't want to do it like 80 here train, and this being test. This is a bad idea because this is not randomly, your data set is not randomly split. So there's certain bias. So you want to take this and take this as your test set and maybe the other as training set. And this randomly choosing, that is determined by random state. So if you use random state, if you fix your random state to 0, then whenever you run this function, it'll always give you the same split, same training set and same test set. But if you set your random state to 1, then it'll give you a different split. So maybe the next time it'll be like these 2 will be the test set and the remaining will be the training set. All right, moving on. So as I was saying, this is a multi-class classification because there are 3 types of flower, but now you're using logistic regression, which is a binary classifier. So I think someone mentioned this before in the previous lecture, that how you can use binary classifier to make it into multi-class classifier. You either go with the 1 versus all or 1 versus 1, which is, I won't go into detail, but you can use a group of binary classifiers to do multi-class classification, and simply doing this will let you do that. So you've instantiated the logistic regression function, which is logistic, and then you train it. So you can see that it's the same API. It's just training. And what I did here is I just used the first 2 columns among the 4 features, right? If you remember the slicing, what I'm doing is I'm taking all the rows and I'm only taking the first and the second column, which is first two features. And Y train is, let's see what the shape of the Y train is. Y train is 120, so because I was using 0.2. So I guess, oh, even if it's multi-class classification, logistic regression receives a vector formed Y labels. So it could be like label 0, label 1, label 2. So if you look at the contents of the Y train, it's 2, 1, 0, like 2 being Virginica, 1 being versicolor, 0 being iris something else. So because there were three classes. So this is your Y label. And you can train your, 네, 나중에 솔루션 올려드릴게요. Yeah, so now you can train your model. So this actually is trained. And then, all right, we're kind of running out of time, but maybe we can do one more quiz. So can you import support vector machine, then train it in the same manner that you've trained logistic regression? You can probably assume that it's going to require only 3 lines of code because you would need to import support vector machine, you need to instantiate it, and then you need to fit it. All machine learning models in scikit-learn go through the same phase. So first of all, what you need to do is you need to sklearn SVM, see where the SVM classifier resides, where it lives. Maybe it's not under linear model. It actually lives under SVM sublibrary. So it's support vector classifier because support vector machines can be either regression or regressor or classifier. So it's SVC. So you'll import from sklearn.svm, you import SVC, and then you instantiate it and you train it. You fit it basically. So just gonna copy paste mine. Looks like this. So you call it, you import it, you instantiate it, and then you fit it. Very simple. And here you can, so as I haven't gone into the support vector machine classifier details in the previous class, but there you can use something called Kernel Trick. And the Kernel Trick is what increases the power of your SVM model, just like the capacity of your model. And here we're just gonna use a linear kernel, making this SVM model a linear model, just like logistic regression is a linear model. And then you fit it, and it'll fit nicely. No problem here. Now you want to calculate and test calculate the test accuracy. You already have the test. You split your data set into X train and X test, right? So now you have this unseen data set, which is X test and Y test. And can you calculate the accuracy of your classifiers, either logistic or SVM? Can you calculate the accuracy of your model using the predict function on the test samples, X test and Y test? Please copy paste this. So I've fixed the random state 1, 2, 3, 4, and I've also fixed the random state 0 here. If you have to follow this so we can compare if you guys have coded correctly and then getting the right test accuracy. So this has to be 0, this has to be 1, 2, 3, 4, this has to be 1, 2, 3, 4. Can anybody give me the test accuracy of logistic regression SVM? yes, solution 당연히 업로드 해드릴 거예요. Don't worry, I'll upload the solution version after this class on class. All right, so we've reached 12 o'clock. So if you have any other schedule, you can leave freely whenever you want. We'll just go a couple more examples before we end this class. Kianmai 7333. Not quite what I'm seeing. Maybe you use a different random state. Oh, I'm sorry. Maybe that's correct. I'm sorry. There was a bit of a mistake on my side. Yep, 7333. Yep, 7333. Yeah, mistake was on my side. So is that the accuracy of logistic regression or SVM? It doesn't really matter because they show the same accuracy actually. Seven three three three. So unfortunately, 7333 is not a high accuracy because the data set is really simple. It's 100. I mean, the size of the data set is simple, but there are only 4 features, and the problem itself is super simple. You can easily get more than 90% test accuracy. The train accuracy would be, of course, 100% because it's train accuracy. But test accuracy, the accuracy that you get on unseen data set, you can easily reach more than 80%. And all right, so let me just fill this in. So you use SVM and Logistic, and you get 733333 for both cases. You can do the same thing with actually score function. I'm not sure if you've actually used a score function or you did calculate like this. So you just count the number of times you got your prediction and the true label are correct, and then you take them. So if you do this, this will be a bool variable. It will be just a numpy array of trues and falses, and you convert it to float value, which will be converted to true being 1 and false being 0, and then you mean it, you average it, and then you get 7333. And you can do the same thing with score function. Actually, score function is the accuracy. So print score, print svm.score x test white test, like this. And I'm sorry. Yeah, because we've trained the classifier using only 2 features. I should have gone like this. Yep, 7333. So score in the classifiers are accuracy. Yeah, sure. Okay, so Youngjun Choi. Yep. Okay, so that's how you use score. That's how you use accuracy, actually. No, all solutions will be given, entire thing. And I'm actually gonna go through the decision trees as well, since for people who have enough time. This is also super simple. I mean, you can do this on your own. You only need to have 3 lines of code to import a decision tree, instantiate it, and then fit it. You go through the same process. You Google Sklearn decision tree and see where decision tree lives. And now it lives under sklearn.tree, and then you call decision tree classifier. So you exactly do that. You do that. So let me copy paste mine. You do that, and because decision tree classifier is too long, I just renamed it to DTC. And then you instantiate it. And there are a couple of arguments that you want to give, which is, first of all, max depth. So depth of your classifier. Remember that this decision tree is a tree, so there's a depth. Like, you know, there's this is depth 3. Depth, is it depth 2? Like this is depth 0, depth is 1, depth. Maybe let's call this depth 2 tree. If you use depth 3 tree, then there will be another depth, another layer underneath. And what that means, what increasing the max depth means is, what does that mean? Does it increase the power of your model or does it decrease the power of your model? Anybody who, yep, of course, it's increasing the power of your model. It increases the how the expressivity, like how much data you can describe. If you have a longer tree, if you have like a gigantic tree, then it'll better, you know, dissect the feature space basically. I mean, here we're only using 2 features, so the feature space is 2-dimensional. So there's a 2-dimensional feature space, and like certain like iris versicolor will be like scattered here maybe, and iris virginica will be scattered here, and something like that. And if you use a long, like a deeper tree, then you can draw a lot of like boundaries like this. And now this can be virginica, this can be virginica, this can be virginica, this can be versicolor, this can be versicolor, like very nonlinear, very, very nonlinear decision boundaries. Yep, because as I said, increasing the power of your model, which is basically here, increasing the depth of your tree, leads to overfitting, as I've shown you in the previous polynomial regression. Maybe next step 3 is not enough, or maybe next step 3 is already overfitting. You can try that out. So I'm gonna fit a tree, and then let's get the score for the tree, which is 0.6. What happens if we use R2? I mean, if we use next step 2? 5 sixths. Okay, maybe that's not enough. Maybe we increase to 5. Okay, 633 is better than before. Maybe 6. Okay, now we're reaching 7. By the way, you should never use the test set. You should never use the test set for tuning your hyperparameter. I'm tuning the hyperparameter, which is the next step. And I'm doing that based on the test set, which you should never do in practice. Never, ever. You should have a separate validation set and use that validation set to tune your hyperparameter. And then once you've tuned the hyperparameter, that's when you actually evaluate your model on the test set. How does each node in this tree decide which branch to take? Yeah, I'm not really sure on that, because as I said, I'm not a tree expert. You use something called cart algorithm to build a tree. So once you've given a data, you need to build a tree to explain the data or to classify the sample, right? And in order to, and you need to, and learning the shape of the tree or the structure of the tree, you use cart algorithm. It's a very, very old algorithm. It's a very reliable algorithm. In fact, I think Sklearn uses cart algorithm, or maybe does it use M5? Fit. Doesn't say what kind of algorithm it is using. Not cart, M5, no. I guess it doesn't really explain. All right, maybe there's like an in-depth tutorial in the user guide. Okay, so I'm sorry, it's not M5, it's C5. So tree algorithm, there's like cart, C5, ID3, and I don't really know how they operate. Yeah, there are some simple explanations here. So the very first tree was developed in 1986, so it's a very old algorithm. Oh, Rushda has given us a bit of a brief explanation. Calculate impurity using Gini index to choose each branch. That's classification criteria. Oh, maybe the question was not how to train a tree, how to take a route in a tree. So in that case, then Rushda's answer is correct. Wonjun's question, but Professor, you said validation set is not used usually nowadays since data set is large. No. That is, we don't do n-fold cross validation. So to answer Wonjun's question, I said that you don't do n-fold cross validation these days because the data set is too large anyway. So the test set is large on its own. So you already have enough statistical power to get an unbiased performance and evaluation of your model. I hope that the distinction is clear. You should always split your data into train and test, and maybe even validation if you want to tune your hyperparameter. Mario Chen's question, scikit-learn is an optimized version of the CART algorithm. However, scikit-learn implementation does not support. Oh, okay. Yeah, thanks for the explanation. All right, moving on. So that was 3 popular classifiers: logistic regression, support vector machine, decision trees. And actually, logistic regression, if you expand it into multi-class classification, then that becomes a maximum entropy classifier. And maximum entropy classifier is the same as support vector. It has the same power as a linear support vector machine. One maximizes, so support vector machine maximizes the margin between the boundary and the sample. Maximum entropy classifier maximizes the entropy, basically. And they both guarantee good generalization performance. It's like the other side of the coin. All right, so moving on. We want to try out one more thing, actually. So before, we use only two columns, first two features. But what happens if we use all the features? Can you get more than 7333? Hopefully so. So there was some. Okay, like training took too long times. But you can ignore this error. Now, once you've trained it, you want to test it. See what we get. 1.0, so perfect classifier. So if you use all features, then you get a perfect test accuracy. That just explains how easy these tests, this classification task is, this iris data set. So you don't want to make it too trivial like this. So that's why I started with only 2 columns. So let's just keep it that way. I'm gonna make it more interesting. Oh, 7333. All right. So the final, so yeah, here, yeah. So using various model options, features, and the score, because support vector machine. If you look at support vector machine, is it here? No. Is it here? No. All right. Sklearn, SVC. If you look at support vector machine, there are a lot of parameters in your constructor. So C is a regularization parameter. The regularization that I talked about. And I said that you can use something called Kernel Trick, which increases the power of your support vector machine. Keeping kernel to linear kind of like, restricts its power. But if you use polynomial kernel or radial basis function kernel, then you're basically increasing this increase. It's exactly like, transforming your linear regression to polynomial regression. You can do the same thing in SVM. You can transform your linear support vector machine to polynomial support vector machine, or maybe even like infinite dimensional support vector machine, something like that. And there is something called gamma, which is a coefficient for controlling the power of your kernel. There are a lot of stuff. Toll is like when to stop optimizing your support vector machine. You need to, you iterate, you update your support vector machine parameters iteratively, numerically, and setting a toll like ensures that you reach a certain performance. If you're interested in support vector machine, you can read the user manual here and see what kind of options you can give. So the option being here, like kernel, instead of using kernel, we can use RBF. and then see what happens. See if we get a better score. It's the same score, unfortunately. Maybe if we use poly of degree 4. Oh, it's even worse. All right, so that was a bad idea. Anyway, you can see that like changing the options for your model will definitely change the performance of the model. Like even this, like changing the depth of the tree was also affecting the outcome. All right, final thing. So the final quiz is: can you draw 4 scatter plots for each model's prediction and the true label? So we need 4 scatter plots because we need the scatter plots of the true label, which is I'm gonna start. Let me give me a second. So yeah, using the test cases. So using X test and Y test, you do know the true label, which is the Y test. So can you draw 1 plot using the true label Y test, and can you draw 3 more scatter plots using the predicted Y labels by logistic regression, support vector machine decision tree? Maybe I should have put it here and then let's push it one by one. So we want to see the truth, ground truth first, and then, and then the C logistic regression is prediction, SVM's prediction, and decision tree's prediction. And what you want to do is, I think everybody's seeing the correct thing here. I hear that it is broken. The link is broken for myself, but I hope that everybody else is seeing the ideal 4 scatter plots side by side. Maybe I can give everybody like 5 minutes. I mean, what you want to do is you want to have 3 colors, right? Because there are 3 classes. There's iris versicolor and iris virginica, and whatever the other thing is. I'm not sure if that would work because then the colors would be. Would that work? Does that work? I haven't tried that actually. Okay, that's good. That's good to know. Then your code is better than my code. So we already have an answer. That just makes it too easy for the other students. Let's try that out. So I guess the function scatter, PLT scatter, recognizes that each sample has different colors. Oh, yeah. Now that I think of it, the color C can receive vectors. So maybe that's okay. Start with the ground truth. Let's just copy paste everything here just to quickly see if that's working. Yeah, it does work. It's the colors are a bit weird. I guess different colors are okay, as long as you can distinguish between the colors and distinguish between the classes. I think that's because the colors now C equals 0 is probably black, maybe? C equals 1 is like cyan, and C equals 2 is yellow. All right, so, well, I mean, x test and x test y hat. So I guess you need to change the y hats for each scatter plot, subplot, because y hat is, I'm sorry, y hat. Oh, you shouldn't be using y hat. You should be using y test, because y test is the true true label here. Okay. Oh, maybe Pagyong's already knew that. All right. So. All right. So yeah. Now okay. Now I'm seeing the actual color. All right. For this, okay. So y hat. Let's just use y instead of using y hat. We'll use this. What we call this y logistic, and we'll call y SVM. And I need this from the tree, y tree. Okay, y tree. And then oh, maybe I should use linear kernel, linear depth. Oh, that's weird. Oh, right, I'm using. Let me just print the scores all together. Yeah. No, just forget out the scores. No, we do need the scores. Yeah. All right, so we're back to 7333s. Now we want to plug in y logistic for logistic regression subplot, y SVM for your third plot, y tree for your fourth plot. See what that gives you. Good. Now, you can see that there's a boundary. I mean, let me. Oh, by the way, did everybody get this plot correctly following Pagyong's code? It's a very simple code, actually. That's a pretty smart code. Yep. Okay. Good. All right. What we want to see here is that basically a classifier. What classifier does is drawing a line in your plane, in your feature space. Now, since we trained all classifiers using only the first two features, you can see that we only trained all classifiers using first two features. So all the samples are now live in a two-dimensional space. So that's why we can draw plots like this, right? If we're dealing with like higher dimensional features, like 100-dimensional features, then we need to somehow compress it into two-dimensional space using PCA, something like that, and then do scatter plot. But here we started with two-dimensional feature space to begin with, so that's why we can just just directly draw the scatter plot. And now, as I said, the only thing that a classifier does is drawing a line in the 2D plane in your feature space to distinguish between one class from another. So what the ideal line would be one line that distinguishes between this class. Let's call this class 0. This is class 1, and yellow are class 2. And the ideal line would be drawing a line here and then drawing a nonlinear line, like, yeah, I don't know how you can draw a line. Yeah, you need to be really specific. Yeah, there's no way you can draw a perfect line. Yeah, this still doesn't work. I don't know how I would draw that line. Yeah, if you allow some errors, then let's call this 2. If you would allow some error, then maybe you can draw like this. maybe like this. This is even nonlinear. This is like there's like a turn. You're taking a turn. So, and even with that, you have 3 errors in your boundary. So it's a hard problem to begin with. It's a hard problem, and unfortunately, because it's a hard problem, the classifiers are not doing a very good job. I mean, the classifier is doing a very good job differentiating between the first class and the rest, like here, 0 and 1 and 2. But because they're all like mixed together, the best a logistic regression can do is drawing a linear line like this. This is the best it can do, because the only thing it can do is draw a linear line. It's because logistic regression is a linear classifier. So this is the only thing that it can do. Same for support vector machine, because I was using a linear kernel. So because I'm using a linear kernel, it can draw only a linear line like this. And okay, I'll answer the questions a bit later. So, and if you move to a decision tree, it is actually, decision trees are nonlinear classifiers, because as I said, it can draw a lot of lines in your 2D plane, like a checkerboard, like a grid, and then assign different classes within each grid or each cell. So the deeper the tree, the more lines it can draw, and the more nonlinear it becomes. So here, move this a bit. So here, the decision tree is drawing a line probably like I'm not sure if it's drawing a line like maybe like this. Like here, this is clearly a nonlinear decision, because you can't draw a linear line to include this yellow thing. So it's clearly a nonlinear line. So maybe it is doing something like this, maybe. Yep. Maybe like this. Yeah, this could make sense. And then it is assigning within each cell, like class 0, maybe class 0, class 1, 1, 2, 2. But still, the power is not enough to actually hash out all the single like yellow lines, yellow samples that is encapsulated, it's surrounded by the blue samples. So you need way much more power to do that, to fit nicely into it, to perfectly classify the test samples. It is a hard data set to begin with. If you only use 2 features, then there's no way you can perfectly draw a line. So it is underfitting. And one of the ways to remedy underfitting was to one easy way was to increasing the power of your model, but another way was to adding more features, right? So if you add more features, then it'll not underfit anymore. And you've seen that when we used all the 4 features, you get test accuracy of 1.0, the perfect score. So now you get the lesson, right? All right. So let me just answer this a couple of questions. 고청의 데이터를 PCA를 해서 시각화하는 건 왜 거기까지밖에 안 여쭤보시죠? 재기님 질문 하시다 마신 건가요? 그렇군요. 죄송합니다. 텐서보드 테스팅 교수님. So the question is, if you want to use PCA or some dimensionality compression algorithm and visualize, if you want to visualize it, is TensorBoard the best choice? I don't use TensorBoard a lot because if you're dealing with small data, small amount of samples, then using Matplotlib is definitely easier to handle your data set and manipulate the figures and all that. TensorBoard is useful when you're training your model, and as you train, as you go, you want to see how the performance changes. Like if you want to see how the loss decreases or how the accuracy increases, something like that. If you and your model and you're training your model like for like a lot of iterations, then you want to use TensorBoard for that matter. But if you once you've trained your model and you just want to visualize the model is what the model is doing on like some test cases, then you know Matplotlib is probably a better way to go. And I'm pretty sure TensorBoard is not as expressive as Matplotlib. I don't think you can draw like weird looking pie charts or bar charts using TensorBoard. Maybe I'm wrong. I haven't used TensorBoard in a really long time. All right, shouldn't the ground truth be with all the data set like PLT, scatter? I'm sure, yeah, you can do that. I just used test set only to see what the model is doing on the test set. If you use training set, you can use the training set to see what the model is, what the model has learned on the training set, and see if they're drawing a beautiful looking line. Yeah, there's no reason you shouldn't do large X, large X, the entire thing. Young Fucho said, is it correct to have all the scatter graphs are the same because given decision tree graph looks different from the... No, of course not. So because the reason that we're using different classifiers is to get different types of performances. So if all classifiers show the same performance, then there's no reason to develop different classifiers, right? So it is here it's just that the data is really small, only 150 samples, and the feature space is only 2. So that's why logistic regression and SVM are deriving the same solution, it's drawing the same decision boundary. But compared to that, decision tree is clearly doing a different thing on its own. So it's natural that you see different decision boundaries among different classifiers, and that's what you want to see actually. Daniel Sachi. What is that for? Oh, nice. Okay. All right. So, okay, let me reproduce what Daniel Sachi just shared with everybody. You draw a line like this. Oops. Yep. So this perfectly classifies between this different, separates between the blue lines and the blue dots and the yellow dots, and you can see that this is a very weird looking decision boundary. So you probably need a very high order polynomial function or some neural network. Basically, I think neural network is a better choice. 모델이 구분한 경계를 플러팅할 수 있나요? That's a good question. So what you can do is you can feed your model the entire grid in your 2D space like this. So you can go linspace 0 to like linspace 4 to 8, and then linspace for x is 4 to 8, linspace y is like 2 to 4.5, and then you create a very dense grid, or dense dots, basically like millions of dots in this space, and then you feed that dot into your classifier, and then you can see where it makes the decision change, where the decision changes between certain coordinate and another coordinate. Oh, actually, someone just shared this decision boundary picture. Yep, that's exactly what I was saying. Yeah, this is a beautiful looking decision boundary. Oh, so interestingly, logistic regression and support vector machine was learning a different decision boundary. It's just that, they are similar enough to give us the same test accuracy. And decision tree is doing a very weird thing on its own. 성민이 혹시 그 카피 페이스트가 어려우면 그냥 코드 스샷 찍어가지고 또 올려주실 수 있나요? Okay, that was really fast. Thank you very much. Oh, it's something called mesh grid. Okay, so there's some function in NumPy called mesh grid, so that you can, sample. You can sample a lot of dots in a 2D plane, and then draw this, and then put it through your put it through your classifier to see where the line is drawn. Let me. What is it? Downloaded somewhere? Oh, it is downloaded. Okay. All right, so this is the end of the practice session 2. So we have spent 40 more minutes. All right. So if there's no more question, yeah, we'll end the class and then return to, I think that class number 3 is about PyTorch. Maybe, yeah. Anyway, yeah. If there's no more question, we'll return next Tuesday. And as I said, I'll upload all the solutions on Classum after this. 네, 감사합니다. All right, bye-bye.